Okay, so hello everyone. My name is Dimitris. Today, as Susanna said, we will go through the third chapter of deep learning with Python. And let's see the title and the what we will see today. So, Introduction to Keras and TensorFlow. These are the chapter contents. So we'll take a closer look at TensorFlow, Keras, and what will be the relationship between these two. We will also see how we can set up a deep learning workspace in case we don't already have your workspace. And we will go through some main concepts of TensorFlow and Keras and how core concepts of deep learning translate to specific objects when we code in Keras and TensorFlow. So let's start with TensorFlow first of all. What is TensorFlow? TensorFlow is a Python-based, free and open source machine learning platform. So it was developed primarily by Google, although nowadays it's many third parties and it's a big community that contributes to the development. The good thing with TensorFlow is that the important thing is that it can compute automatically the gradient of any differentiable expressions. And we saw the previous chapter that this is in the core of deep learning because we use this for backpropagation and fast for the training, for the learning process. And another important thing is that it can run on different hardware. For example, different CPU architectures, GPU, TPU, and again, this is very important because due to this, we can run bigger experiments, deeper models, so we have better results. Also, the computations can be distributed to many machines, so we can have a cluster of thousands of machines nowadays, and TensorFlow can handle the information flow between all these machines during training or inference. And the last thing I want to mention regarding TensorFlow is that it doesn't support only Python, which is the main language, of course, but also C++. You can use in JavaScript. You can use TensorFlow Lite in case you want to run something on edge devices, on phones, on different architectures. So it's pretty much, actually, TensorFlow is not only a library, it's more a platform. It's a vast ecosystem of many components. And although in this book, we will deal only with the library part, there are many things that you can explore. For example, there is the TF agents. If you are interested in reinforcement learning, there is the TFX. If you want to manage your ML workflow better, TensorFlow serving, again, in case you want to move your models, your trained model to deployment for production. Other things like the TensorFlow Hub, where you can find models, pre-trained models that you can use as a starting point for your application. So there are many things. Again, in this book, we will focus only on the library. So this is more or less a very short introduction to what is TensorFlow. Let's see what is Keras now. So Keras comes on top of TensorFlow. So here you can see a figure. At the bottom, you have the hardware, as I mentioned before, it can be CPU, GPU, or TPU. And then you have TensorFlow on top of it. So TensorFlow will deal with all the low-level things like the tensors, the variables, the tensor operations, the automatic differentiation that we saw, some distribution strategy in case you have multiple machines. So all these are handled by TensorFlow. And then you have Keras on top of it, which deals with things that are more useful for the deep learning engineer, for example, like the layers or the model. How do you define the graph of your model? How do you define which optimizer, which losses you want to use, if you want some custom metrics? So all these are the high-level components that Keras deals with this. So Keras, in one sentence, is a deep learning API for Python built on top of TensorFlow. The good thing with Keras is that it's convenient to define models, to define layers. It's plug and play. It has very easy API, and the the way you interact with it, it's very easy to learn. So for me, it was, well, it was not the first one, the framework that I learned, but it's actually my favorite. I think that it's very easy for beginners to use it, and it's also highly productive for even expert users. It's very easy to define your experiments, just a few lines of code. It has over 1 million users as of late 2021, and the users range from academia, so you have academic researchers, you have engineers in the industry, you have data scientists, companies. In the book, you can see some comments that use Keras and TensorFlow, like, of course, Google, Netflix, Uber, organizations like CERN or NASA. And of course, you have companies, I mean, hundreds of startups and bigger companies. So Keras, let's see now what is the relationship between Keras. We saw what TensorFlow is, we saw what Keras is, and now let's see the brief history between Keras and TensorFlow. So it started back in 2015, and actually it's strange because we said that Keras was built on top of TensorFlow, but actually Keras predates TensorFlow by 8 months, so you can ask how it's possible. Keras initially started as a backend, as a higher level for Theano. So Theano was one of the first, if not the first, framework for deep learning. It was developed, I think, in Montreal. And it had these core characteristics that I mentioned before, like the automatic differentiation, and it would run both on CPU and TPU. So Keras was built in order to support Theano, and then when TensorFlow was published in late 2015, Keras started supporting also both Theano and TensorFlow as backends. Then the next year, so up to 2017, we had more backends that were supported by Keras, like CNTK from Microsoft or MXNet from Amazon. But the thing is that, so there was this year that there were many frameworks for deep learning, but then it started stabilizing. So now CNTK is not developed anymore, I think. MXNet is mostly for internal use. Theano is not supported, is not developed anymore. So currently, for present, Keras only supports TensorFlow. And actually in 2018, Keras is so popular that Keras becomes the TensorFlow's official high-level API. Because they found out that actually most of the TensorFlow users use it with Keras. And the big step for Keras was in 2019 when we had the first new version of TensorFlow 2.0. And from 2.0 and afterwards, Keras is already integrated in TensorFlow. So you don't have to install Keras, Keras comes with TensorFlow. So this is a very brief history between Keras and TensorFlow. You can find more details, of course, in the book. So now that we saw what TensorFlow more or less is and what Keras more or less is, let's see how you can use them. So how you can set up your deep learning workspace, again, in case you don't already have one. It's more or less two advices. First of all, use TPU instead of CPU. If possible, it's much faster. It can be 5 to 10 times faster when you run the same thing, special training on CPU, in some cases even more. And there are different options for TPU. First of all, if you have it, good. If you don't have, you can buy one. I know that the prices nowadays, the last months, become higher. You can find a good one for $1.5 or $2,000, maybe. An easier solution would be to rent one. So there are many options out there. For example, AWS or Google Cloud or Paperspace are some of them. There are many more. The prices are not that high if you want to run an experiment for a few hours. And there is the option to use a free one, which is a very good option. We are lucky to have it. Actually, I was pretty lucky the last year because I actually used Google Colab. We'll see Google Colab today, actually. There is Paperspace Gradient, so there are some free options. They provide GPUs where you can run your deep learning experiments. Now, regarding the operating system, it's preferably to use Unix, so Linux mostly. You can use Windows. It's not that it doesn't run. TensorFlow supports Windows and Keras, but the author and the creator of Keras proposes to use Unix because there are sometimes some connectivity issues with the connectivity between the GPU and TensorFlow. So, and I'm not sure about Mac if they even have GPU. So this is how to set up more or less different choices for your GPU. Now we will see how to run the code. So again, based on the book, the preferred way to run your deep learning experiments is Jupyter notebooks. In case you're not familiar, we will see what Jupyter notebooks are today. So it's more or less a way to edit your code in your browser. Usually when you edit your code, you have an IDE, an environment like, I don't know, PyCharm or VS Code or something like this, where you have your code base, you change the code, you debug, etc. In case you don't have something like this, you can use your browser, just Chrome or Safari or whatever, Firefox, and it's pretty helpful. Personally, I also use it very much, both this and code. You can add markdown text for annotation or comments. You can add code, you can interchange them. And the good thing is that you can run blocks of code independently. And it maintains the current state in main memory. So this is a big difference between this and the scripting. When you write a script of code in Python, you have to rerun the whole thing. So if you want to change something or check something, you have to make the change and run again. So for deep learning projects that it might take lots of time to run one script, it's a pain. Yeah, it's not very helpful. So with Jupyter notebooks, it's very easy. You just run a code, change something, run again, etc. And Colab. So I mentioned Colab before when I talked about the free GPU options, and Colab is actually a free GPU with a Jupyter notebook. So it's a free Jupyter notebook service online. You don't need to install anything. You just click on this link, so colab.research.google.com, and it runs entirely in the cloud. So you don't have to have a GPU. You don't even have to have a fast computer, just a browser. It's free. It supports both GPU and TPU runtime. It's quite limited, of course. I mean, first of all, the GPU card is not the high end, and you cannot run forever an experiment. I mean, there are some time limitations. Now let's see what this actually looks like, because it's quite interesting. So if you click at that link, you will end up at something like this. So here you can see different examples, your recent notebooks that you have used, or you can define a new notebook. So let's see how we can start a new notebook. You click here, and then it will start initializing the new notebook. So everything you see here is just in the browser. I don't run something now in this environment on my computer. So here you can see that there is this thing. These are cells, so blocks of either code or text. So you can see that you can add more code cells or more text cells. You can change them. For example, you can write, it supports markdown, so you can write, I don't know, build this. And here you can run code. So you can write something like, don't know, 3+4, and you can click here, run, or you can shift enter and run it. So we wait for this to connect. Another important thing is that you can change the runtime. So if you go to runtime, change runtime, you can select between running on CPU or acceleration with GPU or TPU. If you want to run something regarding related to deep learning, I suggest running on GPU. So you just click here and you save. Let's see, let's actually do this, save. So it's allocating again, it will initialize the session, and then you can run the code again. So this is very helpful. The other thing with Colab specifically is that it has many libraries that are pre-installed. So you can do something like import NumPy, and it will run because NumPy is already installed. And the same thing with TensorFlow. So you can write import TensorFlow as TF, and again, it will run. Now, in case there is a library that we don't, that is not already pre-installed, for example, if you want to run a project on medical images, okay? So medical images usually come in DICOM files, and the popular Python library to handle them is PyDICOM. So you usually run import PyDICOM, okay? So you see here that it will not run because PyDICOM is not pre-installed. So in this case, what you have to do is install it. And the good thing with notebooks is that you can run bash commands. So it's like running on your terminal. You just add an exclamation mark in front, and you can run commands like whatever, it's the usual command like ls or make zero, this stuff. And you can, of course, install a new library. So you can run pip install PyDICOM, and it will locate it, download it, and install it, and then you can import it as we. So now it will not throw an error, it will just import. So it's pretty useful. Again, personally, I used to use a lot this Colab in the past. Runs quite good. I mean, GPUs are not that bad, especially for small experiments. You can save your files, you can mount your, here you can see that you have the files, you can upload the file, download, you can mount your Google Drive. Very, very easy. So this was more or less the Jupyter notebook. So this is Jupyter notebook and in Colab. Now let's continue. This is how you can run, but let's see what you can run. So let's go back to TensorFlow now. First steps with TensorFlow. Again, TensorFlow deals with a low-level tensor manipulation. So you have we will see how we'll do this. We will see what tensors are again, what are the variables, what is the difference. We will run some tensor operations, mathematical operations. So we will see again the gradient tape that we saw at chapter 2. And then we will move to Keras. We will see again how to define the layers, how to inherit from layer this time to create a new layer. Loss functions, optimizer, metrics, and the training loop. So let's move to the tensors. First of all, constant tensors and variables. Let's see the constant tensors. It's quite easy if you are familiar with NumPy to use TensorFlow tensors. So for example, if you want to create an all ones tensor, in NumPy you write np.ones. So it's pretty similar. You write tf.ones and you run this and you get the tensor that is created, the TensorFlow tensor in this case. So you can see it's a 2x1. You remember how the d type argument, it's a float 32, and it's ones. The same way you can, again, same as NumPy, you can create zeros, so tf.zeros, you can create a tensor full of zeros. So this is pretty straightforward. You can also create random tensors, and this is quite useful when you want to initialize the weights in the model. You usually initialize with random weights. So tf.random supports different random distributions. Like for example, the normal distribution, you have to define the mean and the standard deviation. By default, of course, it's 0 and 1. And you define the shape. So if you run this, you get this tensor. If you run again, you get another random tensor. So pretty straightforward, again, similar to NumPy. And of course, it supports other kind of distributions like the uniform distribution, again, mean and max value, the shape, very easy to use it. Now, apart from this, there are some differences. So we saw some similarities with NumPy. Now let's see some things that are not quite same and what you can do for this. So in NumPy, you can create an array, a tensor, and then you can assign values to parts of this, either a slice or an element. So for example, here we create ones, and then we assign value to the 0.0, 0.0. Now, you cannot actually do this with tensors in TensorFlow. So you can, of course, create TF once and this will run, but if you try to assign using this, it will break. And the message is that this object does not support item assignment. So, and it's important to know this because if you're going to go deeper and define some things by yourself, you will, I mean, for me, it's a pain how to deal exactly with how to make changes. So one important thing is that tensors, you cannot do this. What you can do, however, is that you can use variables. So TensorFlow supports variables that you can assign values to them. So tf.variable instead of tensor. And then you have to pass the initial value. So you can randomize, like for example, tf random normal, you define the shape and that's all. So this is how you define a variable. And the good thing with variables is that you can assign values. So it's quite different. It's not equal with slices. You have the variable, the tensor variable, and then you call the assign method, and then you assign the new method, the new values. So you see that we created one with zeros and with random values, and now we have assigned it is ones. One important thing, it doesn't create a new tensor. For example, you cannot write 4 here, okay? It will break. The idea is that it changes the values of the existing tensor. So bear this in mind that you have to assign values of the same shape. Now, if you don't want to change the whole tensor, the whole variable, you can assign values to specific slice or to specific elements. For example, if we want to change only the first one to 3, it's doable. So there are things that you can do, there are things you cannot do. You just have to get familiar with this, and you almost never don't have to deal with this. I just show them because it's important to see them at least once, but you usually don't have to deal with this kind of stuff, except if you want to define your own train step or your own loss or your own layer or something. Also, you can use in place operations, so you can assign and. So you don't have to write v equals v plus something. You can do it in place, which is important because we don't have to pass the whole object. So you see, it works. Now, we saw how we can define tensors and variables. Now let's see what we can do with them. So some mathematical operations, basic ones. Let's create a tensor. And then we can take the square of it, we can assign, we take the square root of it, we can add 2 tensor, we can multiply 2 matrices, or we can in place multiply. So these are perfectly valid mathematical operations with tensors as it would be with NumPy arrays. So pretty simple. You use them usually again when you want to define your own loss, for example, or something like this. Now, these are simple mathematical operations. Let's move to something that we saw the last chapter, which is gradient tape. And again, it's very in the core of what TensorFlow does. So let's see again how we use gradient tape. Let's define a variable, initialize it with some value. Again, this is a scalar, so rank 0 tensor, if you remember from the last time. And here we open the scope with TF gradient tape as tape, and every operation we want to follow to what the gradient of has to be within this scope, so in here. Here we just take the square of this, and we assign it to result, and we take the gradient of result with respect to input variable. And of course, it will be 6, I mean, with 3 squared, so 2 times 3. So this is more or less how gradient works. We saw some examples at the previous chapter. The good thing is that you can again, never use it, but you can use nested tapes, gradient tapes. So for example, if you want to use it in at a physics experiment, you have an object that you drop it and you want to you have the equation of the position with respect to time, then you can calculate the speed, which is just the derivative of position with respect to time. And if you use another gradient tape, you can take the acceleration, which is the gradient of speed with respect to time. So you can do things like this. Again, I have never seen double gradients to be used. Maybe there is some case study. Now, let's, now that we saw more or less what tensors are, what variables are, how we can make some mathematical operations, and how we can use gradient tape, all of them, we saw them again today. Let's run an end-to-end example. So we will use, we'll create a linear classifier this time. Last time we created an image classifier. Now it will be much simpler. We will create our own data. So let's generate two classes. Very simple, just random points on 2D. So X, Y coordinate, that's all. And each point will have a level, positive or negative. Let's create the points. So we define how many samples per class, 1000, and then we create the negative and the positive. So we just pick randomly from this distribution. The multivariate normal takes the mean, so where it is centered, and the covariant matrix, which is what is the shape of this distribution in space. And of course, how many points we want. So we will create two distribution, two set of points, same covariant matrix, so same shape, but different, they are centered in different places. So this is at 0.3, 3, this is at 3,0. So let's create our input data, the samples, and now let's create, now we have two NumPy arrays, and we want to create the input data. So both of them together. And it's very simple, we can just stack them, vertically stack them, and the input data that we will use is now this and this stacked together. So these are our inputs. Now let's generate our labels, and we will set as labels 0 for the negatives and 1 for the positives. So the code is again quite simple, we just stack together, vertically stack, zeros for one set of points and ones for the other set of points. Okay, just how many points we have at each class. So we have our inputs and the targets, and they are both NumPy arrays, NumPy tensors. Let's see what they look like in the space. So it's easy to plot them because it's in 2D. So we generally, when you run a Jupyter notebook, like I do right now, you use matplotlib pyplot to plot things. In this case, we have points in 2D space. So we use scatter. These are the X coordinates of each point, and these are the Y coordinate for the points. And we define the colors. So the colors will be the numbers. So zeros for the first points and ones for the second points. Let's see what this looks like. And here you have the points. So again, these are the points of the one set, and these are of the other set. And the colors are based on the label that we define, 0 or 1. Now let's see how we can distinguish this. So what we want to create is a linear classifier, which is just a line that separates these two sets, okay? So let's create this linear classifier. Since it's a line, it will be a simple function. So the input, the XY, the coordinates, times something plus something. So the W here will be what will be the slope, and B will be, okay, how we translate it, more or less. So let's try to minimize the square of the difference between the prediction of this linear classifier and the targets. So we take the difference, and then we take the square of the difference, and this is the value we try to minimize. Now, this is how we define the variables of our classifier. So again, we have to define this one and this one. And for each point, we just multiply by this and we add this. We get the prediction. We want the prediction to be close to the real label. The dimensions, it's a 2 input dimension because we have points with 2 coordinates. So 2 for input and 1 output, just 1 label for output. So we define both W and B to be variables. And we initialize, so for W, we have uniform from 0 to 1 with this shape, and for B, we have zeros with this shape. Now that we have defined these TensorFlow variables, and we can use them and we can update them. So the idea is to find the correct W and B so that we have the line to separate the plane correctly. Now let's see the forward pass. We define a function model. It's not even an object. It's just a function that takes some inputs and use these defined variables and applies this operation. So we apply matrix multiplication between the inputs and W, and then we add B. Let's run this one and move. So now we have to define the loss function. Again, we said that we will try to minimize the square of the difference. So this is what it looks like. We will take the outputs of the model and the targets, and between them, we take the difference of them, and we take the square of them. So for each point, we have this number, this loss. We have 2,000 of them, and then we just take the average because we want the mean squared error. So TF reduce mean will take the average of all these numbers. And now we have everything we need to define our train step. So we have defined our TensorFlow variables, again, variables because we want to change them. We have defined what is the forward pass, so what is the family of equations in which we will try to find the solution. And we have defined what is the loss, according to which we will find the final solution. So let's move to the train step. And the train step again is pretty straightforward. We saw something similar last time. We defined the learning rate. It's quite big because we will run batch gradient descent, not mini batch. So we will use the whole data set at every step. We will open a gradient tape scope, and we will run the inputs in this function. So we will use the variables, we'll get the predictions, we'll pass the predictions and the targets in this square loss, and we will take the loss. And then we just want the gradient, the derivative of the W and B. And in order to get this, we call tape.gradient. And we define the gradient of what with respect to what. So we have a list of objects here. So we will take a list of 2 objects here. And this is our very simple optimizer. So we have these derivatives, this gradient, and we just take the previous value and we subtract from the previous value the gradient. And we multiply it by learning rate to make smaller steps. Again, we have seen something similar last time. Finally, we will return the loss to see how we go. Now let's run the batch train loop. So for each step, we will run for 40 steps. We take the inputs, all the inputs and all the targets. So these are the coordinates. These are the labels, 0s and 1. Compute the loss, update internally, and print the loss. It will be, yeah, it is pretty fast. And it's very, very simple. And you see that we start with a big loss and then we end up with very low loss, which means that probably it worked. Now let's see, let's try to plot the predictions. Again, when you want to get the predictions from a model, you pass the batch of samples, in this case, all the samples in the model, and then you call it, and then it returns the predictions. And here we can get the, we can plot. So again, we plot the X and Y coordinates of the input data of the points. And what changes is the color. So now for color, we will have this. So for the predictions, if the prediction for the specific point is less than 0.5, it will be 0. If it's more than 0.5, it will be 1. And based on this, we will have the different colors when we plot. So yeah, it seemed pretty good. I mean, we separated this and this. Now in between, there might be some points that were different, but this makes actually quite good sense, which means that we found the separator. So we found a line. Now let's see what this line actually looked like, how we achieved this separation. What we did is that we defined this W and B, and every time we have a point, we multiply W and with the point and we add B, right? This was our model function. But what does this mean? What is this prediction? So what we actually do is that we take W, which is just 2 by 1, so 2 numbers, and we matrix multiply with these 2 numbers, and we add B, which means that we have some W1 coefficient, number times X coordinate, plus W2 times Y coordinate plus B. And the way we use this prediction to classify is that we said if it's less than 0.5, it's class 0. If it's greater, it's class 1, which means that we just take this and we compare it with 0.5, which means that there is actually a line when we set it equal to 0.5, which is the separation, right, of the plane. And this is the equation of the line. So W1 times X plus W2 times Y plus B equals 0.5, which means that we can take the function of Y with respect to X, and this is the function of our line in this case. Now, let's see what this means. Let's create some points X, and then take the Y points for each one of them based on this equation. So we create the Y's, and then we plot not only the points, but also this line that separates the plane. So all this was to explain that there is a line, this specific line, which is our linear classifier. So everything we did the last 5 minutes or so is that we separated the plane with this line to the 2 classes. Now let's see how we can do this using actual neural networks. Okay, so the anatomy of a neural network and how we can understand the core of Keras API. As I mentioned before, and we will connect what we just did with Keras, layers is the building blocks of deep learning. Layer is a fundamental structure, a data structure in neural networks, and each layer takes some input, applies some operations, and then returns one or more tensors output. Now, each layer has a state, and the state is just the weights of the layer. And it's important to know that different kinds of layers are good for different types of tensors, of tensor formats. For example, there are layers that accept specific type of tensors, and they are better, have specific characteristics that are better for specific tasks. Now, let's see one of the layers in Keras. So if you remember last time we had defined the naive dense. And the naive dense, we defined it standalone, so as a new class, but this time we will see how we can implement it as a layer of Keras. Again, as I mentioned before, it's in the core, the layer is in the core of deep learning, and thus it's in the core also of Keras. So everything in Keras is either a layer object or an object that is closely related. It closely interacts with some layer. It can be the output of a layer or the input, which means tensor or variable. It can be the loss function, which takes the outputs of the layer. It can be a model, which is a graph of the layers. And again, this object, this layer, Python object, has the state, which is the weights, and the computation, which is a forward pass. So if you define these two, then you have the definition of a layer in Keras. Now let's see how we can create a new layer in Keras. And this time we will not have the naive dense, we will have the simple dense. The difference is that this class, this object, will inherit from Keras.layers.layer. And this means that we gain all the functionality that it offers, the layer template offers. So let's see. First of all, we have the constructor. The constructor is the signature, same as before. So we have the number of units for this layer, and we have the activation function. The first big difference is that we initialize the superclass so that we gain the functionality. We assign the values to the instance, and then instead of having one class, the Dunder call class, as we had before, we have 2 new classes. We have the build and the simple call function. And we will see why we have these 2 and we don't have the Dunder call. Now, the build function takes as input the one input, the input shape. So the shape of the input tensor to this layer. And from this, this includes both so this is a batch, okay? So the input shape is the shape of the batch, which means that the first dimension is the batch size. We don't care about this, we care about the size, the dimensions of the features. So this is how many features we have as input. And here is how we define the weight of the layer, in this case, the simple dense layer. So when you want to add weights to your layer, you use this self.addWeights. You can, of course, define a variable, so tf.variable, as we saw before, but this is the proper way to add the weights, because now you have to just define the shape, and you have to define the initializer, which can be just the string, and it knows where to read which function to use to initialize. So we define two weights, W and B, we add them as weights with, again, the same shape as before, and the same, more or less the same initialization. The other function method that we define is core, that takes the input tensor and runs the forward pass. So the forward pass will be exactly the same as before, just matrix multiplication between the inputs and the self W, and then we add self P. In case we have an activation, we run the activation and we return Y. So many similarities with naive tensor and naive dense that we saw before, but now there are some differences, and let's see how this helps us. This helps us because when we define a new layer, the simple dense, we don't have to define the input shape. For example, here we can define one with 32 units. And then if we create an input tensor with 2 samples and 784 features, now we don't have to pass this value to the constructor. We can just use this myDense directly on this input tensor. And somehow the model knows exactly what to do, knows how to define this correctly. So let's see, to make sure that it can run. And indeed it can run, so it outputs a tensor of 2 samples with 32 features each sample. Now, how did this manage to do? Again, if you remember, in naive tensor, we had to define this 784 before. So this is a main difference, one of the main differences, of course there are more, when you inherit from layer, from keras.layers.layer, is that it can automatically infer the shape. So it can build the layers on the fly. You don't have to build them explicitly. And this holds also for the built-in layers. For example, the dense layer, you just write it like this. You don't have to define the input shape. So the layer outputs a tensor with the first dimension to be transformed to 32 outputs now, okay? And this is how you can define using sequential, a model with sequential layers, and again, you don't have to define the input shape. So now we saw an example using naive classifier, naive dense, and now we will see how we can define this using Keras sequential. So here you can see I can stack various layers, and I just define this. In comparison, last time we saw the naive sequential with the naive dense, and if you remember, we had to define these numbers. Okay. Now, what happens? How does it know? And of course, here it might seem simple, but if you start dealing, as we will do in the next chapters, with more complicated layers like convolution, it's not that simple to compute what will be this input size, because you have something like you have the size of the core, you have the size, if you use strides or not, if you add padding or not. So it's not very straightforward how to compute this. So it's very useful, and especially if you have a big model with hundreds of layers, you don't have to make these computations. It does it automatically. And how it does it schematically is this. So when you call the layer, it calls actually the Danter call, this function, this method. And this method internally does something like this. So the first time that you call the layer on a tensor, it takes the input tensor, And if it has not been built yet, it builds itself, which means that it's called the build function with the shape of these inputs, which means that at that point, it initializes the weights. So until you run the first tensor on this layer, it doesn't initialize the weights, which means that it doesn't occupy any space. And also that it doesn't, it now knows what will be the shape of the weights that it has to construct. And then it calls our call function on this. Of course, the call actually does many more things. It deals with the distribution strategy, if we want to have the same layer on different machines, etc. But one of the things is also this build and call. And this is why we don't define, when we inherit from layer, the dunder call, we define the build and the call functions methods. Now, we saw how we can define properly a Keras layer. Now we will see how we can define the models. So in neural networks, again, everything it is, a neural network is just a graph of layers. It's layers connected to each other. And this thing in Keras, it's the model class. So the same way we have the layer class for the layers, we have the model class for the models. We already saw the sequential way of building a new model. So this is just stack of layers. The one layer connected to the one after and after and after. Now, this is good for simple architecture, but if you want something more complicated and more realistic, you cannot just stack layers, you make something more complicated. And for this, you have two ways to do it in Keras. The first one that we will use a lot is the functional API. And the second one is to subclass from the model class, the same way we subclassed we inherited from the Keras layer class. And it's important, this structure, this graph, because the topology of the model defines the hypothesis space of the model, of your experiment, which means that your solution will be one of these within this hypothesis space. So the way you structure the layers and the model encodes all your assumptions and your prior knowledge for the task and the input data. For example, if it's images, then you know that it's image, you know what it means if it's invariant to the different parts of the image, etc. So you use specific layers and specific structure. And here you can see the structure of a part of the structure of transformer architecture that is very common nowadays for language, and we will see how to do this, I think, chapter 11. But the idea is that you can not do this with sequential. You need something different. This is why we have the functional API, and in case we need it, the subclass model. Now, let's say that we have constructed this model, and next step is to compile. If we want to use the fit method, we have to compile the model. And again, we saw before, to compile, we need these three elements: loss function, which is the quantity that we try to minimize; optimizer, which determines how the network will update the weights based on the loss function; and the metrics, which is just a number that shows if we are successful or not. They monitor the success of the training, for the training, and the validation data. We will see what validation data is next slide. And this is how we will define the model. So again, we will use sequential, just one layer, one desk layer with one output, same as the linear classifier we saw before. And now we compile using a specific optimizer, mean squared error. This is the same loss function as the one we used, and a metric. Now you see here that we use strings to define what kind of optimizer or loss function, but actually you can use an object. So Keras comes with Keras.optimizers that holds many different kinds of optimizers, loss functions, and metrics. So you can use all these that are built in. And the important thing, so this block is equivalent to this block. It's the same thing in the end. The important thing with this is that you can actually define your own custom loss and metrics, and you can write something like this. So model.compile with my custom loss and my custom metrics. And this is quite useful in some cases, as we will see. Now, there are many available options. You almost never have to write your own optimizer. You just use one that is predefined, either built in Keras or you find the code. Losses, again, big variety of different losses and metrics for different tasks that you might have. Now, the question is, okay, we have that many losses, but how do I pick which one I want to use? So we will see in more detail, depending on the task, how to pick your loss function. And it's important to pick the correct loss function. Again, choosing the right loss function is very crucial, and there is a common example that is mentioned sometimes. It's a theoretical example, of course. Let's say that you built an AI and you want it to, you set as a target, as the function, to optimize, to maximize the average well-being of all humans alive, okay? Let's say that this is your target. Now, this AI system might choose to kill all the humans and just keep some of them and focus on the well-being of the remaining ones, right? So this would be actually very valid based on what you asked from the model. So the average well-being isn't affected by how many humans are left, right? And this example shows that the model would just try, all that the model knows is your loss function. It just tries to find any way it can to minimize your loss function. It doesn't care what you have in mind. It cares about what you asked it to do. And I know that it might sound a bit silly or too theoretical, this example, but it's many times that you see that, okay, you have in mind a task, you define the loss function because this is the correct thing to do based on the bibliography. And then you see that the model misbehaves or does something different. And then you have to change your loss function or change the data or something. Now, there are some guidelines. For example, if we want to do classification, like the linear classifier with two classes, we use binary cross entropy usually. You can use, of course, the mean squared error. If you have many classes like the images we saw in the previous chapter, you can use categorical cross entropy, etc. We will see more loss functions in the next chapters. Now, when you have defined the loss, the optimizer, the metrics, you have compiled the model, then you can run fits, you can train the model. We saw this before again. It's things that we saw, but we say again so that it's more familiar to you for the next chapters. For fit, you have to define the data that you will use, so both inputs and targets. Usually it's NumPy arrays, like in this case that we will run now, or it can be generators of data, it can be TensorFlow datasets. We will see these objects in the next chapters. Other than that, you have to define how many epochs you will train for and the batch size. Again, the model takes batches of data, not simple samples. So how big will be this mini batch? Let's call the fit function now based on the NumPy arrays that we have defined. Remember, this is a model with the one layer, the dense layer. This is the inputs, the coordinates of the points that we defined before. These are the targets, zeros or ones for the two set of points. We run for 5 epochs with batch size 1.8. You see it runs very, very fast and it seems to work. So let's see what it returns. So when you run model.fit, it returns an history object. Now this history object has a field called history, which is a dictionary, Python dictionary. And what it has is two different things. One is the loss and the other is the accuracy in this case. So this is the metrics. And here you can see that we have for each epoch, we have the different, the loss and the metric for each epoch. So 5 epochs, we have 5 losses and 5 binary accuracies. Now let's continue. It's a good thing to talk now about the validation data. So monitoring loss and metrics and validation. Let's see how we can use the validation data argument and what is this. So when you train a model on some data, you don't have to evaluate on the same data. The problem is that the model has already seen this data. It might remember the data and not extract some pattern. So you always evaluate the data, the model, on data that it has never seen before. And this is why we split the data to train and validation, at least. So let's define again the model, same thing here, we compile it. The difference is here. So first of all, we randomize, we shuffle the input data, and we want to shuffle the same way the inputs and targets. And then what we want to do is to take a split of it for validation. In this case, we just take 30%. So we define how many samples we want. We want 30% of the inputs. And we keep from the shuffled inputs, the first, this number as validation inputs and targets, and the rest as train inputs and targets. Again, this is in order to validate the model on data that it has never seen before, okay? So what we do is that we call model.fit. These are the same, but now we see that we use this validation data argument. And here we pass the validation inputs and the validation targets. So this is a tuple with two elements. We run it again, and we see that now we get not only the loss and the binary accuracy for the training, but we get also the validation loss and the validation binary accuracy. And you see that this is something new, and this is because we use this validation data argument. Now, if you want to validate evaluate your model after you have trained it, again, you do it on new data. And in this case, we will use the val inputs and the val targets. So the way you validate to evaluate your model is you call the model.evaluate method that takes these two arguments. And also you can define the batch size in case it's very big, you have to split it. And it returns the loss and the metrics. Now, we saw how we can define the model, we saw how we can train the model, we saw how we can evaluate the model, and now we will see how you can infer from the model, how you can use the model to get predictions. And the way to do it is to use the predict method. So model.predict, you pass one thing, which is the inputs, the batch of the inputs, and then this returns the predictions, okay? And you can define the batch size if you want to split it in small batches. So let's see what this looks like. This looks like numbers, okay? And if you remember by the definition we gave before, if it's greater than 0.5, it corresponds to the positive class, otherwise to the negative class. So this was more or less what I wanted to present for this chapter. Let's summarize to see what we saw and then move to the questions. So a short summary, we saw, we talked about the TensorFlow and the Keras history, what is each one of them, how they are connected to each other. We saw the main elements for TensorFlow. So TensorFlow, again, is a numerical computing framework. It can run on different hardware, CPU, GPU, or TPU. Keras is the standard API for deep learning for TensorFlow, of course. And the key elements for, we also saw how you can build your own workstation. You have to use, for example, you can use GPUs, and we saw some choices that you have for free GPUs. We saw how Colab works, which combines Jupyter Notebook with online on the cloud computation with GPU. And we also saw some of the key TensorFlow and Keras objects. So for TensorFlow, we saw what tensors are, again, how you can define them, how you can, it's similar to the NumPy tensors, the NumPy arrays, but what are also the differences? For example, we saw variables if you want to change values. We saw how you can apply some operations with tensors, how you can use, again, gradient tape. And then we have the Keras. So for Keras, we saw the layer class, the layer template, how you can inherit the layer template and use to define your own simpletons in our case, and how you can build a model using the sequential way. And then for the Keras steps, these are the main things, the main methods you have to remember for a model. You first call model.compile. And with model.compile, you define what is the optimizer, you define what is the loss function, and you define what are the metrics. And then you have the model.feed, which is where you pass the target and the inputs and the target. and you can also pass the validation data. And then you can train the model, calling model.fit. And we also saw two more methods, two more functionalities. So model.evaluate to evaluate the model on your metrics, where you pass both the inputs and the targets, and model.predict to predict on new data, and where you just pass the data. That was it. Thank you very much. This was the end of the presentation.